So I'm Sylvain from Stockley, and I'm just going to introduce the session for tonight. So first of all, welcome here. Welcome for this 5th meetup, I guess. We are very happy to have you here, and yeah, very looking forward to these meetups. Can you hear me well? Is it okay? Cool. All right. Okay. So first of all, I've been asked to talk about a bit of feedback from the last sessions. What you liked was mostly about the pizza, of course, and the friendly atmosphere and the fact that we can meet other Rust, or not Rust actually, developers tonight. And you've also asked if it was possible to present about async topics. And actually, Thomas works also at Stockley, and with the second speaker tonight, is going to talk about async tonight. And also, so following previous feedbacks, we're going to do the talks probably in English today at least. All right, so tonight, two speakers. Quentin, who's going to start. Quentin has been coding in Rust for 5 years, I guess, now. And he's working at Rayon Design. He's been working there for 1 year and a half. And then Thomas Bessou, who is an engineer at Stockley, who's going to talk about async. And so I guess each talk will be about 20 minutes long, and then there will be a session of about 10 minutes of questions, same for both talks. And then we can have our beer and pizza time together. All right. Then I guess I let you the mic.
Okay, so good evening, everybody. So tonight I'm going to speak not about async, sadly, maybe, but that would be for the talk afterward. I'm going to talk about Rust, WebAssembly, and how to use it with whatever framework you want, because we all know it's changing every 6 months. So a bit of an introduction. So I'm Quentin. I'm working as a software engineer at Rayon Design. So for those who are wondering, it's not linked to the Rayon crate. It's a completely different thing. But we do work in Rust. So I understand how this might be confusing. But we are a space design collaborative tool on the web. So I'm going to do a short introduction about what is exactly WebAssembly, if some of you don't already know, because it's a bit of not widely used yet, or not widely known. We're going to talk about how to do WebAssembly and what tooling is available for us in Rust. And I'm going to show you a bit of two apps, like a really small toy app, which has the code organization to how to use WebAssembly, Rust inside a front-end project, and probably a bit of how we use it at Rayon, so a bit at scale. So first of all, so what is WebAssembly? So really quickly, WebAssembly, so it started its life as async.js, which was a subset of JavaScript optimized for performances. So it was a bit of a trick to be able to run JS faster. And afterward, it evolved into a full instruction set, but it's like a virtual instruction set. So it's a bit like bytecode for Java, for those who know that. So, and its goal is to be compact, portable, and secure. And so as an example, so on top top right, you have like a small, really easy Rust code, and how you would write it in WebAssembly just behind. So yeah, it's using like a stack machine architecture. So it's a bit different from like classic ISA, which are using for example, x86, which are using register for operations. So a bit of example of use cases for WebAssembly. So for example, Skia, the Google library, the Google rendering library for 2D is using WebAssembly for some of its tools. And for example, you have also a version of TensorFlow, which is distributed as a WebAssembly. And when WebAssembly is interesting is, for example, you already have like a big application which is written in something else than JavaScript, in C or in C++, and you want to use it on the web. And so you can compile your existing code base in WebAssembly. This also includes application that needs to be portable. Like you need to have like a different version of your tool to have like a native version, a web client, or you want to run it on a web server. And also you have application with performance or security constraints because the WebAssembly memory is apart from your regular JS memory. So you have like a separation of concern on this front. And also, when you want to get to use nice properties of your language, for example, memory safety of Rust, developer experience, and you really want to use that, but you still have to ship like a web application. Something that I really want to emphasize is like WebAssembly is not a silver bullet. JavaScript is actually really good for some things. DOM operation, JSON serialization, or like regular API calls. It's not the time to rewrite your whole code base in Rust just because you can, especially if you're targeting the web. So be really mindful about what you want to rewrite and to use WebAssembly for. So the Rust tooling for WebAssembly. So how we do to have like my Rust code to run on WebAssembly. It's actually very simple. It's just like a compilation target. So the same way you're going to compile for your Linux machine or your Windows machine or macOS, you're just going to say, I want to target WebAssembly, and that's it. So it's a bit scary because once you do that, like for just, so below is just like the previous code we saw. So just A plus B, and I put it in C, and you can see we have over 9,000 lines of generated code. So obviously, this is like a text representation of like the code, but WebAssembly is at first a binary, and you can disassemble it to read the instruction and to be able to analyze it. But all of this is like the nice property you have from Rust. So error messages, panic, invalid arguments, what happens when you call unwrap on an error, this kind of stuff. You need to have like those instructions in your WebAssembly code, like for your program to actually do something when those cases appear. Okay, so now I have a WebAssembly code, awesome. But like the issue is, how do I exchange data between my JS environment and my WebAssembly environment? Because I just said like the memory in WebAssembly is separated, right? Sadly, the only thing you can pass around is integers and floats. That's it. So you have to either copy your data bit by bit, which is really annoying, or pass pointer into that are pointing to things in your linear memory. So you have complex object, you need to pass a pointer that is going to reference this complex object. This is the code you have to write in JS to be able to just initialize your WebAssembly memory before even loading your WebAssembly module. It's really annoying. It's really It's a lot of stuff, and it's going to change every time your memory map layout is going to change. So it's no good. We can't do like that for production. It's fine for simple programs, but for more difficult things, it's not good. So we have like thankfully the Rust team has think about us, and they introduce Wasm by Gen, which is like the tooling in Rust to be able to easily do WebAssembly. It gives you JS functionality in Rust, so you have access to DOM operation, console log, performance monitoring, whatever you want. You can export your Rust class as modules in WebAssembly and use it directly from your JS environment, which is actually what we want. It allows you to work with rich types objects, with rich types, so strings, object, and not being able to, not being obligated to just pass raw pointers across your memory. And also it has nice things for production. It's able to generate your TypeScript types to be nice to your front-end developers, because if you generate JS without types, they're not going to be really happy. And the nice thing about it is the only thing you need to do is to use the Wasm by Gen here above your data structure, and basically that's it. So you might be asking, okay, the code I'm showing you right now, it's a little weird, but with this high position, those who are who have done TypeScript in the past, when it was a way of annotating interface, might remember this annotation. I will talk about it a bit later. In Wasm by Gen, we also have WebSys, which is basically a big crate which gives you all the DOM API that you might want and to use it directly from Rust. So for example, if you want to create a WebGL environment, for I don't know, a space design tool where you want to draw stuff on the screen, you can create directly all those stuff and pass your memory object to your WebGL directly from Rust, which is actually nice. But you also have access to really more simple things. So the console log, obviously, because it's strongly typed, you have as many console log functions as you can have number of arguments. So at some points, it's getting really hard. On the subject of building, because you also have Wasm Pack, which is basically wrapping Wasm by Gen, and another library which is called Wasm OPT, which can optimize your WebAssembly bundle to be able to be smaller and more efficient. Actually, we had we used it for a while, and in the end, we just write our own Xtask to be able to build it. So we are not using Wasm by Gen, Wasm Pack anymore. We are using the Wasm by Gen API and the Wasm OPT directly into a Xtask. And this allows you to really understand what's going on and to have you know what's going on, and you have a Xtask that you can personalize for your needs. So a bit the limitation about Wasm by Gen and WebAssembly in general. Typing arrays is not possible with Wasm by Gen right now. You have to pass either you pass uint 32 arrays or the types that are available, so 8, 16 arrays, which are actually typed in JS. But if you have more complex data structure, for example, my position that I had, which was not that complex, it was just X and Y inside the struct. But if you have an array of that, you can only say to your JS, okay, it's an array. I don't know about it's an array of what. So it's not very usable on this front, but you can still use generated TypeScript types in your front-end code to say, no, I know this is an array. And I know this is an array of position, for example. there is some, so as I said earlier, there is some really weird thing you need to do to have like nice usable TypeScript types. So we're going to look at enums, for example, which they released a new version on Tuesday, actually, that improves that. So this talk is already not very up to date. And also, something that you need to be aware of is like getting data across linear memory for complex types can be costly. So because you're still going to pass around pointers, and sometimes it's going to actually copy your data into the JavaScript memory. So you need to really do performance testing and memory analysis to see what you're actually using, because you can have like really big bundles and really big memory usage when you initialize a WebAssembly module. So just I'm going to get back a little bit. Yeah, so for example, for this apposition, it's not nice. We are going to see how to use it in production. Actually, not put Wasm by Gen annotation on all of your native types in your Rust crate, because it's going to be annoying. You're going to be dependent on how you want to export your types for your main core Rust crate, which is not a good thing. So I'm going to show you very quickly if I can. So the organization of a small app, which I called Space, which is actually a monorepo. I don't know if you can see. Oh, it's on the top. So you have your crate, which is actually a workspace. And you can have your core, which I called Space Engine here, which is just, so in this example, it's just a library that is using an ECS engine to do collision detection between different shapes. So, for example, you have like a circle, a square, you calculate their position, they are going to move around on the screen, and every time they collide, you have like a component which say, okay, like my two shapes are colliding. So it's really simple. I have my core things with my component, resource, and system. And I have like an API that allows me to interact with like with my ECS. So for example, it allows me to start my engine at the start of my program. And also, for example, my geometries, I can say, okay, I know an idea of a geometry. I want to know which kind of geometry it is, which is just a type geometry, which is so a bit weird because it's a struct geometry with a geometry type, and inside you have an enum. So like classic stuff. Okay, but I don't actually depend on Wasm by Gen in this core crate. It's just my library, it's just my engine. I want to use all the nice Rust pattern I know. I want to use this kind of enum with data structure inside. And all of that is not going across very nicely. So I created like a second crate, which is Space.js, which is actually like my JS API, which is going to depend on Wasm by Gen, and which is the one I'm going to interact with from my front end. So for example, we can see my geometry API, which is just a get geometry, and it's going to return a type of iGeometry, not geometry directly. And why? Because you can't export enum with data structure inside. So you need to create like a type which has a geometry type, and actually my data, which is inside my data structure. So you're going to write a lot of, you're going to implement into a lot, so to get your data across. But it's nice, it's on the side, it's not in your main crate, so you have like all your dependency are here, and it's dumb code, but it's so it's a lot of code, but it's easy code to write. It's usually very straightforward, and actually you could imagine writing some macro to get it like done really faster. And after that, I just have like my Xtag that is going to export my JS API, and I have like a package which is like a so it's going to generate like a JS package which is called Space Engine, and it's going to be used in my React API. So for example, which is going to get my geometries, and as you can see, I have my engine, which is my API interface. I'm calling them with React context, but you can store them in whatever you, state you want. And you can see on every frame, I'm going to check the position. I'm going to try to get is my geometry colliding with another, and I'm going to react on that directly. I will show you the app running at the end. It's not really interesting. It's an ugly app. It was just for the organization. So your main problem now is just your API design. Like, so this is what I was explaining. You have to write nice types to be able to interact with your front-end developers, and so they have like the correct thing. And you are not limited in your expressiveness in your main trait. So you can do Rust whatever, like however you want. So a lot of easy code, but necessary. And also, which is nice, you have a change of internal type. You just have to rewrite your transformation layer to return like the same public type. And you have like a nice separated API. And everyone is very happy. One last thing that is really can be complicated is to stay in sync with what is happening into the Rust and your WebAssembly engine, because you're going to interact. So getting information out is actually quite easy. You actually can request the state of your engine on every frame, for example. It's not that costly. We are doing it in production. The issue is what is happening when you have like a form, when you can put new information for your entities that are stored into your WebAssembly. When that happens, you can have like a desynchronization. For example, you have like a multiplayer app where someone can say, my geometry is going to move at 10 meters a second, and someone else is going to say, no, right after, it's 15 meters a second. You have to say, okay, something changed into my engine. I need to refresh my React state. There is two solutions, basically. I mean, there is multiple solutions, but the easy one is just to try to keep a big global state of everything that is happening in your engine, but you have like your state twice, once in your WebAssembly, once in your React application, and that can get out of sync if you're not careful. So yeah, at first it's not too difficult to maintain, but when you have a state with like thousands of entities, it can be difficult to maintain and also really costly. So what we've done at Rayon, so I'm going to show you like the app. Obviously, I don't have it ready because it would be too easy. Okay. So basically what you're seeing is like a React app and like the Canva on which I can draw, for example, walls. It's a WebGL Canva, and the engine that is drawing on it, it's an ECS written completely in Rust and distributed as a Wasm bundle. The issue is, for example, I'm selecting a wall. I have properties on my wall, and this is like React components, right? It's so I'm going to change the length. It's obviously going to react on my Canva, but I can also directly edit my Canva, and this is going to make my React application change. And so this is not as evident as it might seem, because you need to be able to say, okay, something happened on the Canva, I moved the wall, I need to refresh this component. And to answer this problem, we used state machine. So we used actually X-state. So basically you have like a big state machine with events, which are the only way to write into the engine memory. And this way, you can say, for example, for my example of geometry with velocity, I can write a function that is going to say, to wrap my API call to my set velocity, and the event is going to know you need to update the properties panel. And so this way, you have a global state of your React application, which is easy to follow, and you can have like a granular control over which components are rendered. You can have like as many flags as you want, and you can refresh like big part of your subtree, or only one component which have like the information you want. So something I did not talk tonight, but I think it's nice to mention. Some Rust frameworks are actually used for front-end development. So for example, Vue, which are distributed as a WebAssembly. So I didn't talk too much about ECS, but it's a really nice pattern for this kind of problem. So we are using specs at Rayon, but I invite you to look at Bevy also, which is like a more video games based engine, but like the ECS pattern is really well done in it. And also more advanced state management pattern. And for 3D or stuff like that, so for my demo application, I use React Free Fiber because I was really lazy and I did not want to rewrite like a complete WebGL wrapper in my Rust demo. So yeah, some resources and credits. So the Art of WebAssembly, which is like really good. Obviously the Wasm engine guide. I want to thank also my team for like the inspiration and the first state of the code base, and Stockley for the invitation. Thank you, everyone. So questions.
Yes. Thank you for this very informative talk. I do have a question regarding the interaction between JavaScript and Rust, especially this synchronization problem. So yeah. I guess the issue here is that it's quite difficult to synchronize between React because it wants to do this virtual damping, and you have Rust in the other side. Why didn't you write the interface like what video game developers do in C++ or Rust?
So I'm going to repeat the question so it's recorded. So the question was why we didn't write our interface directly in Rust, so in WebGL and in React. Because first of all, it's very costly to do so. Like it's a different kind of problem, and you need to because right now our engine at Rayon is only a geometric engine, and it's really tailor-made for drawing plans and architecture, right? So either you need to use like a different UI library, and also you need to find people that are competent in writing UI library in a low-level language, right? React developer, you have a lot of them. You have a lot of really great React developer, and also velocity. It's important you are way faster at writing UI in React. And it's obvious, and the web is good also at rendering React. So you need to focus only the performance on actually your engine and not like your whole UI on the side. Yeah.
Thank you for the talk. My question is actually linked to the same synchronization of the state. First of all, what are you using exactly to manage all the state? I imagine you need something more advanced than Redux to manage the state in React.
Yeah.
Also, how do you trigger the synchronization if there is the sync, for example, from the UI state to the Wasm state? How do you detect that, and how do you trigger the synchronization?
So the question was about like state synchronization and what do we actually use at Rayon. So we're using Xstate, which is actually like a state management state machine. And basically, so you have two. So we have all those events, right? You have events when you do something on the screen, whatever it is, and this event that is going to ask like the change to the engine and to re-render inside the component, right? And if you change something on an input, it's also going to send an event that is going to rerun, like called a render frame, and which is going to update like the canvas actually. It's not like the canvas is not run on every frame. It's only run on every frame that when you do an action, for example, or something is happening.
So the same way that React behaves when it has to render.
Yeah. Does it answer the question?
Yeah, thank you.
Okay.
Just, if you had to modify the React state loop to, like for the synchronization, I was thinking that you probably had to modify how React handles frame rendering.
No, yeah, so we don't do that. So the only thing we do is we call, so to be more exact, when an event happens, we have a flag that is changing, which is just calling a re-render on the React component. And inside the React component, you have like a call to the Wasm state, which is getting like the actual value.
Yeah, thank you.
Yeah.
Are you following anything about being able to manipulate DOM from Wasm? Do you have any updates on that?
I actually don't. We are not using too much of that. The only thing, like the only WebSys API we are really using intensively is like the WebGL one, because we're only interacting like from our code directly with WebGL, and everything else is exposed through our API. So it's not using the same thing.
So you can interact directly with WebGL, sorry.
Yeah.
In Wasm.
Yeah, exactly. Which is there is a bridge between the two, but yeah, essentially yes, you can. Yeah.
I was wondering if you could say more about the transformation you're doing for enums to make them TypeScript friendly, and especially why it's not done by Wasm by Gen. Is there like a limitation that it cannot be done, or is it in the pipes?
I actually don't know. We experimented a lot of different things actually for how to pass like to generate like a nice TypeScript API, because you can always sorry, just a sec. I'm going to display the code of the geometry ones. Yeah, okay. So basically what we're doing is we're just extracting like the data inside the data structure, and we are putting it like in a different field. So I think it's because it's not done by Wasm by Gen. If I had to like make an hypothesis, it would be because it's not a transparent transformation. You actually have new fields that are created. You can also define with Wasm by Gen. You can define getter, and you can with the Wasm by Gen API, you can also transform names of field. But you have to explicitly make it. So, for example, here my field is just named geometry type, but in Pascal case. And you could actually add like a Wasm by Gen getter, a JS name here, and say, okay, I want it to be called geometry type with a more like a TypeScript friendly type of thing. But I'm not sure, like the decomposition here. You're creating new things, and sometimes here it's easy. It's just like basically you're getting your type, but you still have to write your into method for every type you want to transform. So it's not. I don't think it can be. Some types it's going to be able to write a macro for it. Sometimes you can't. You need to actually write it. Yeah.
Just a quick follow-up. Here you've lost the invariant that a plane, for example, cannot have a radius. So do you have to by hand make constructor functions for every possible shape, so that no front-end developer can create either a plane with a radius or a circle without a radius, or
so
somehow automate it?
So this is like the getter. So this is a getter function. You actually interact. So I'm not sure. Yeah, I didn't create like a set geometry, but if you could, like if you would write like a set geometry properties, you add like you would pass an option, or like you would have to write it by hand and to say, okay, it's and you can actually return also API result, which can error in JavaScript. So you can say, okay, no, you can't do that, it's an error, and it can be handled from the JavaScript side. And actually, you should most of our call to the WebAssembly engine are wrapped into try-catch, because you really don't want your WebAssembly engine to crash, because when it's crashing, it's not recoverable most of the time, because you have like you're basically unwrapping like the whole stack, and it's a nightmare to recover from. Any other question? Yeah.
Very quick question about, are you using some advanced optimization techniques like CMD or multi-threading in WebAssembly?
Right now, no. It's planned to be able to improve our performances, but actually right now it's quite adequate. We can always do better, but we are like focused on production, so it's not time for over optimization yet. But yeah, you can do. Actually, you have like an option, I think, to activate ACMD directly. And also you can run your WebAssembly into a worker if you really want to like offload some computation. But then you have like a whole new things, like a whole new class of problem, off-screen Canva, this kind of stuff.
Then how are you making sure that you are not blocking the thread when waiting for events? As you said, you are waiting for events from the front end?
We are not really waiting for events. It's all in X state, so it's in Node.js. So obviously it's just one thread. It's in the event loop, right? So it's not blocking the event loop, but it's actually I'm not sure. To be completely honest, I'm not sure. Okay, I think that's it. Thank you, everyone.
Good now? Okay. So I'd like to talk about asynchronous and weird asynchronous things you may encounter when optimizing projects, and hopefully that will bring some interesting facts about how to make Rust programs performant, in particular in that domain. And to do this, we're going to follow an example project, which is going to be, we want to read from a Kafka, which is a message queue, and we want to insert that into a Scylla, which is a distributed database. And so yeah, each message in the Kafka queue is serialized in a format called Avro. It's pretty non-essential, and Scylla distributed database is extremely performant. It's written in C++, and it doesn't have all the features of a relational database, but in return it's extremely fast. Now, what are we going to put in the middle of this? My usual favorite answer to this question is just put a Rust binary. You typically have all the craze that you need, and it should be reasonably easy. So for Kafka, we actually have a library binding to the C library, which is the standard in this industry for years. For Avro, you also have a library managed by Apache. And for Scylla, you actually have the Scylla team maintaining the Rust driver. So it should be pretty straightforward with Tokyo. So how do we design that software? So we're going to just read from RD Kafka, have a set of tasks that are going to be dedicated to transforming the message from the Avro format into what we want to insert. And then we're going to have a bunch of tasks, like 1,000 tasks for insertion. And each of those is going to make an asynchronous call to the database to make an insert and wait until it returns to finally commit the Kafka message as read so that it does not come back later. Now, to connect all of these, we're going to just put some channels, and each of these is going to constitute a buffer. so that if one side starts to slow down, its buffer is like, for instance, if Kafka stops sending messages because, let's say, someone else is reading from there, so it starts giving us messages slower, then we're going to have a small buffer that we can take from and still keep using our full CPU to make the insertions. And then we're going to have, if our CPU becomes unavailable because we do some other work, then we're still going to have a bunch of messages already ready for insertion later. Now, what we expect to see in this case is if we cannot read fast enough from Kafka, we expect to have all of our channels empty. And if the database cluster cannot insert as fast as we can read, we expect to have both of them full. Now, what actually happens? And so we implement this, and actually we have no idea because we do not have any way to know what channels are full or empty. We just know that we're running at, let's say, 200K lines per second, and we have no idea if we're efficient or anything. So that's where I want to introduce the first lie that you may have when designing such apps. And that would be the standard Prometheus Grafana combo. You have a great Prometheus client library that has been released like 2 years ago or something. And that's basically all the code you have to put. You instantiate a registry, you initiate some metrics, and then you just add a metrics endpoint to whatever HTTP server you're using. Here in this example code, Axum, and you get this. So, yeah, highly recommend. And what actually happens in our first version of the binary? What we see in our first version is that our first channel is full and our second channel is empty. That means that we're actually not processing fast enough. Wait, what? I thought Rust was performant. That's what I was told. It was supposed to just go fast. As it turns out, it is, but only if you're using it properly. That is by not writing stuff that is about 10 times slower than it should be. Now, let's have a look at how the Apache Avro crate works. What it does is you have your buffer with the serialized message, and then when it deserializes, it first turns it into an instance of this huge enum, which itself contains, depending on the type of data, either if it's bytes, you get a vector of U8. If it's an enum, you get the discriminant of the enum, and a string, which is the name of the enum. So, and then if it's an object, you get a hash map with a string, and then another instance of this enum, which does allocate, which whenever you encounter a field, does fill in a hash map, and which is overall like work that you wouldn't want to do. And then once you have this wonderful structure, then you finally use 30, and you create and you reallocate all of your fields another time. So you're gonna ask your allocator to do a ton of work. Now, what do we do? The same thing as we always do in this case. Rewrite it in Rust. Yeah, I mean, I know it's already Rust, but sometimes it just happens that even projects written in Rust, sometimes it gets rewritten in Rust. So I actually rewrote the Avro deserialization, making full use of the third-day zero copy features, and that means that this and str actually points into the original buffer, so it makes no allocations. And the performance difference we get is about 10 to 20 times. So if there are newcomers, I know that some of the comments for previous meetups have been sometimes the talk are not super new user friendly. So if you're a new user, piece of advice from this: don't be afraid of references. Don't be afraid of lifetimes. This is a mistake I originally made. Like I thought, passing own stuff is going to be easier because then I'm not going to have to bother with lifetimes. Turns out it's actually not the case, because if you're passing owned objects, then they will get dropped at some point and you're going to get annoyed. Whereas if you're passing references, you can just keep them alive all for the entire duration of your program, basically, or your endpoint call, for instance. And yeah, not only you would lose the performance you came to Rust for, but also it's actually harder to manage because preferences just have copy. So okay, now that this rewrite is done, where are we with our projects? At this point, both queues turn out to be empty. So that would seem to mean that actually we're not reading from our Kafka server fast enough. And that feels weird because Kafka is basically just putting all the messages in a big file and then giving you that back. It's just reading reading from beginning to end, and it's just giving you data, and it does not process lines individually really ever. So it feels weird that it would be slower than CLab, which is actually doing a ton of work to handle lines individually, partition them between different nodes, etc. So let's analyze further what's going on in this part, just in case there is something wrong going on there. And so if we look at Kafka, there is actually at the RD Kafka library, which is like industry standard, there is actually an internal queue to that, which we have access to via an API. We can know like how much stuff there is in there. So let's add that to our Prometheus monitoring and have a look. Okay, so actually we are still a problem because Kafka is clearly sending messages fast enough. We're going to have to dig further into the binary. Now this is where I want to introduce another must-have performance investigation tool, and that is perf. So the idea of perf is just that you put this in your cargo.toml, then you run these two commands, and you're done. You open this in Firefox, and you get a wonderful graph. So this is what we get. I'm not sure if it's very readable. It doesn't seem to be. But what we see is notably that when reading a message from Kafka, there is some time that is spent actually reading the message, and a lot of time that is spent calling this function here, clock get time. And you would have no idea, like, why does it spend 70% of its time looking at what time it is? I just want to read a message, right? And it turns out this is because Liberty Kafka makes sure that we, the client, keep regularly polling for messages, and otherwise warns the server that they need to stop sending us messages because our binary is down. So the solution to this, obviously, will be to...
Rewrite.
Yeah, no, not rewrite it in Rust because it's 100k lines, so we're not going to rewrite it in Rust this time. No, it's going to be just a simple pull request, which is only 45 lines instead of 100k. What it does is, instead of looking at the time every time to know what time it is and look if we have pulled regularly enough, we just set an atomic variable to 1, and then another part of the code checks if this is actually getting set to 1 regularly and set it back to 0, so that we know we're pulling. And we get 60% CPU consumption reduction. I hope they will merge it someday. Yeah, so there was actually another thing in this perf that seemed to be taking an unreasonable amount of time from our original project. And to illustrate this phenomenon, I'd like to have a look at another example project designed specifically for this. So let's imagine we have one writer. So writer is writing in the channel and reader reading from channel, which is doing a medium amount of work for each message. And 5 readers, each of them are doing a big amount of work after reading from the channel. And we're gonna have a look at what happens when we use the standard crossbeam channel library, which is when not doing asynchronous stuff. And we're gonna have a look at what happens with async channel, which is the standard for multi-producer, multi-consumer channels in the asynchronous ecosystem. So let's run this and print out some stats about the speed at which items are pushed to the queue. So this is the Crossbeam channel version. We can see that it starts running at 150k lines per second. And then when the channel gets full, it stops and only processes like 95, 1 million, 1.5 million, 1 million. Because the queue is full, and since the readers have too much work to do, it's the readers that become the bottleneck. It is still at 100% CPU even on the senders because of the spin looping, the active waiting that is usually there when you're doing synchronized work with threaded stuff and not asynchronous stuff. So asynchronous should avoid spin loops, so we should get to be more efficient. So let's have a look at how it goes. So in the beginning, it's much faster. We're processing 2.7 million per second. And then the channel gets full, and then we entirely stop sending new messages for some unknown reason. And then the channel gets empty, and we start processing fast again. And during all that time, for some weird reason, Tokyo only uses like the five tasks at 100%, because we have 5 readers, and when we're writing, so that means we have like 4 actually out of 5 doing stuff, and 1 must be the writer, and 1 is always at 0. Weird, like why does Tokyo do that? What's going on? Anyway, on average, we get the same speed. I'm not sure why it does that, so if somebody has the answer, I'm interested. It did not show in my first project, so I don't investigate further. Anyways, same speed. Now what happens if we make the readers faster? Instead of doing big work, let's say we optimize some library, and suddenly they cost 10 times less. Let's have a look at Crossbeam. We used to process at 1.5 million per second before it was full, and now we just process at 1.5 million per second all the time, and the channel is always empty. Meanwhile, the CPU is still at 100% all the time because of the spin loops. What happens with asynchronous channels? Well, the channel is empty, but now it's actually gotten slower. It's at 800,000 lines per second instead of 1 million or 2 million. So we've actually reduced the amount of work that readers do, but it's gotten slower. What happens? What's going on with futures? They were supposed to be like faster, much faster than synchronous work. Well, let's have a look at what perf says again. As it turns out, the writer here spends half of its time sending the message. It's specifically designed so that it spends quite a lot of time building a message, but it spends just as much time just sending. So what's going on? 40% of the total time of the function is spent in notifying the readers. So what happens actually is that when the readers look for a message and they encounter an empty queue, they will set themselves up for wake up. And when the writer sends a new message, it has to go through the list of people that it may need to wake up and call a bunch of Tokyo internals to set them up ready for the next wake up. And that is actually costing a ton of time to our writer. If we compare this with what happens with Crossbeam, there is more time spent in synchronization codes, but overall just waking up other threads is not that costly. If we compare that to what used to happen with our inefficient workers, we can see that when the channel is empty, it just costs absolutely nothing, because the readers just always find something to dequeue, so they don't need to ask to be woken up. Now, what's the solution to async channel being inefficient in this scenario? Well, the solution is, once again, not going to be to rewrite it in Rust, because it's an industry standard with millions of downloads. So first of all, we need to find a design. And what happens if, when encountering an empty channel when trying to read a message from there, instead of immediately setting up ourselves to be woken up by the sender, instead, we just wait. We just wait for a tiny bit. And then if there is still no message, we register ourselves for wake up. It should not really matter, because the next buffers should be full. So we should not negatively impact the ability for this guy to read as fast as it can. And here's what happens. What happens is we get 2.2 million lines per second inserted, which is times 2.6 performance. Our channel stays filled up a tiny bit because sometimes the readers are all asleep. What we're doing, in effect, is that we're preventing each reader from registering itself more than once every, let's say, 100 milliseconds. So we cost nothing to the writer. Yep, and we see our CPU using 100% on the writer and nothing, or basically nothing, on the readers. So where's time spent now? Only where we want it to be spent, where I have explicitly asked it to spend time. Where are we at with our project? At this point, we have all our channels full. We are saturating the Scylla cluster, and there's another story of optimization within the Scylla cluster where it does also spend time doing asynchronous stuff, where it allocates a serialized message, and then it allocates, you've probably encountered, if you are doing async, the one-shot channel. And what this does is it reserves a storage for the response, and then when you're resolving the future, you're putting your response inside that storage, and then you wake up the other guy, and it comes and reads out from this allocated storage. So every time we make a query, we actually interact with these things. We call a bunch of functions. We allocate dedicated storages. We wake up some tasks to get to know when stuff is inserted. So we can see that in perf as well. It takes half of the time. So actually, we can just batch queries. We just make batches of like 60, and it just completely disappears from the graph. So it's the same exact methods as before, which serves as a reminder that, once again, allocations and Tokyo are not that free. Yep. At this point, we're at 2 million inserts per second to our server, which is really nice. Key takeaways. If nothing else, remember from this talk that you should not be afraid of using references, that you should rather be afraid of allocations. They ruin the benefits of using Rust for performance. You just lose 10 times, like factor 10 of performance. Powerful monitoring is actually easy. So if you have an app where you're wondering like how fast does this part go, how fast does this part go, really easy to put in place, go ahead. And finally, if investigating CPU performance, easy command to run, and you get the answer in a nice graph. That's it. I hope that it could help one of you in the future if you need to investigate such things, or that you learned interesting facts about unexpected Tokyo performance in some weird cases. That's it. Thank you. Any question? Yes.
Thank you for the talk. I do have a question regarding the using Tokyo for the runtime, the default runtime for async stuff. I saw that you are using ScyllaDB, so ScyllaDB is written in C#, so it's using a thread per core architecture for ingesting data. There is also Glomio as a runtime in Rust for doing thread per core work. I guess at this high throughput, did you consider changing the runtime completely and using SPSCQs for direct communication worker to worker?
So the Scylla driver is actually relying on Tokyo for all of its own work, so that would have been pretty hard to do. However, there was someone at the previous meetup, I'm not sure if he's still there, who actually has rewritten the Scylla driver, which is separate from the official one, which is meant for much more performance, and that completely destroys the benchmarks. I did stay on the standard one because just doing batched insertions did completely negates the performance downsides of Tokyo there.
I guess my question was more about the whole architecture of using a thread per core architecture for the whole pipeline, not only the driver for that.
The benefits of this is that you control how much parallelism you have at each step. So you get to have like 1,000 of parallelism there, and then you know that you have only, let's say, 16 cores on your machine, so you put 16 cores on the transformation, and then you know that you only have one thing there that can process things because the algorithm is not cannot be distributed. So you put one, and you have naturally all these buffers that come into place. So that's why it's comfortable. Yes, middle, yeah.
Yeah, so about zero cost visualization, I guess you can avoid allocating strings or basic data type, but can you avoid allocating hash maps or more complex objects?
Yes, so in the SERDE deserialization framework, the way it works is it tells you, okay, I'm going to deserialize a field named like this. Please provide me with something that I'm going to send each of the fields to. And then you call the function to give that. And then then SERDE is itself going to call, hey, now in there's this field, and there's this field. So
it's like an iterator of it.
Yeah, but you get function calls that follow basically the patterns of your structs, and you can choose the appropriate fields then. So in this deserializer implementation, we just propagate where we are in the structure of the serialized data, and SERDE takes care of taking care of where we are in the output structure. Yes.
I have a very dumb question. Sorry. Can you go back to the final diagram? Yes. Previous slides. So I'm trying to understand which part infects your program as async, right? Why do you need to go async? Which part? Why do you use async there?
Mostly for the reason that this library provides an asynchronous interface.
Okay.
The library on the right also provides an asynchronous interface.
Okay.
And channels seem to be overall more performant in asynchronous world, more performant and efficient than they otherwise are because when you're not using asynchronous, you have this polling spinning loop feature where in case a message comes soon, it's actually going to actively wait and check if there is a message for a bit, and then only then sleep, which is rather inefficient compared to the asynchronous channel, which ends up being at 2.2 million messages per second compared to the 1.5 that we have with Rustbeam.
Okay, so it's not necessarily because your program was IO bound?
Nope.
Okay.
Yes?
Yeah, I wonder, did you try keeping the same channels, but instead of passing one message per channel item, passing a chunk of messages, which would make that for the same throughput in messages, you have much less channel pops and push, basically. Would that be a hack that could kind of circumvent the issues you had there?
So sorry, I did miss a bunch of the question. So were you suggesting using chunks?
Using channel messages,
yeah.
Messages, the type of a message, you use a channel of an array of, I don't know, 1024 messages, which means that reads are much less frequent on the channel, and so you reduce a lot of pressure you have in the whole task switching of the field. So it's hackish, right? But do you think that helps in a way?
In the very first queue, you have the messages come one by one, and the API is this way, and it's hard to make it so. And then the hard part about this is to complete to know when a given batch is complete, because at any point in time, this guy is going to stop sending messages. And if your batch is not full, you still need to decide to send it. So there's this logic to manage. And if we can make the channels completely inexpensive in another way, it's more comfortable than using vectors. So after optimizing the channel, we get at 5%. So we get at like 5% total time. So it's completely neglectable, and we don't need it anymore. However, this is what I actually did for the Scylla insertion part for the batching. Because we are constituting a batch, so there's this other crate which allows turning a stream into chunks. But if there is no message for a bit, then it still gives you a chunk. Any other question? No. Well, thank you, everyone. Sorry.